There. Hangouts on air. There we go. I gotta mute that. That's gonna cause a problem. All right, welcome everybody. Just a second, we'll get rolling. It's just us. I don't want all this effort to be not for anything. Just run through it real fast.
Well, I think one person is watching.
Oh, is there?
Yeah, on the YouTube channel.
Okay. All right, so let me open. We'll start with question 1. I need to open.
As a reminder, this is we're going to be reviewing the midterm practice exam. And we're going to be going through all the problems. Me and James split the problems, so I'm doing all the even numbers and he's doing all the odd numbers. We can answer any questions. We'll be monitoring the chat that's in the YouTube channels. Oh, I don't think anybody's watching us now.
Yeah, I know.
All right, well, we'll keep going, I guess, because they'll watch this recording later, I suppose. But anyways, so yeah, we'll go through each problem one by one. If there's any questions, feel free to put them in the chat, and we'll try to answer your question. And when we're done with the 9 problems on the practice midterm, then we can maybe answer other questions too. Just type them in, and we'll go from there. All right, James, it's all you.
Cool. All right, I'm just trying to get the practice midterm information open. I will share that screen. So OneDrive, ASU, past classes. 2, 3, 4, midterm, practice. All right, bring up. Hangouts. Present. Share screen. Share. Present to everybody and make sure I stay on. All right, for question 1, we're asked to do some simple signal transformation. We have x of t shown on the plot of the following functions. And then we just got to make these 4 functions transform the x of t to fit the 4 functions below. So I have our x of t drawn right here. And the first is a modification to the t variable. The modification of a t variable shows a shift in period, and it cuts the period in half because it doubles the frequency. Frequency equals 1 over period. If you guys haven't memorized that equation yet, you'll be infinitely familiar with it. So we can see that we just cut the period in half. So instead of going from 0 to 3, we go to 0 to 1.5. And associated points moved back by half. For problem 2b, or problem 1b, we have b of t equals x with a negative t plus 1. So we can see the negative signal flips it along the y-axis, and the plus 1 will shift it to the right. And I get the shifts left and right confused quite often. So I've had a little check I usually do to make sure I did this correctly. So the pencil dash is the original. The green dash is a flipped, and then the blue is swapped over to the final by 1 to the right. So to do this little idiot check I do, we take a look at the graph when t equals -1, which would be right here. Or wait, g of t equals 1. Sorry. So when g of t equals 1, no, g of t equals -1. We have a 1. So we plug the -1 in. So you have the -1 to the -1, which cancels, and then added 1. So you're looking for x of 2. So our original x of 2 is also 1. So you can plug a couple points in, and you can see that, hey, we're good. So for C, we're going to go, it's x of t times the unit step function u of t minus u of t minus 2. So that means we're only going to be active for x of t in between the values of t equals 0 to t equals 2. So the graph there is just the cutoff. The little drop here was cut off because the function was cut off. And the last one is just the sampling property. The only time delta t minus 1 is active is when t equals 1. So we have just a spike of amplitude 1 at t equals minus 1. So this amplitude is equal to whatever the value of x of t is at that point. So at when time equals 1, we're equal to 1. If say x of t were equal to 3 or 2 or something, then the amplitude would be 3 or 2. And that's pretty much it for problem 1. Moving to Woody.
Okay, I've unmuted myself, and I think I am projecting my screen now. So let's get into problem 2. Problem 2 is talking about signal properties. And the question itself asks, under what condition is a discrete time signal x of n or a continuous time signal x of t periodic? Determine whether or not the following signals are periodic. If the signal is periodic, determine the fundamental period and justify your answer. And then we're given 2 signals to take a look at. Part A is a continuous time signal, and part B is a discrete time signal. The expressions are very similar. They're just sinusoids. But what makes a discrete time different from a continuous time is that discrete time is akin to taking samples at equal intervals, as opposed to continuous time. You're not taking discrete samples. You're taking basically the entire function as a whole. Good example of a discrete time system would be, like something that's hooked up to a clock pulse in, let's say, a computer, and it takes a temperature reading every 50 milliseconds or something like that and reports it to a computer. Versus continuous time would be something that's more analog and not something related to a computer, for example. Like maybe a continuous wave radar is just watching a video feed come in from an antenna or something. Anyways, that's a little tangent. So let's actually get into problem 2 and start solving these. So I have my notes here. First, let's examine the definition of something that's periodic. So this is the same definition that you've been given in trigonometry classes and calculus classes and elsewhere. And basically, you've seen this before with sinusoids, but in very generic sense, something is periodic if you can define a function x of t, and you just apply a transformation to that, that variable t. You add a constant such as big T. Essentially, you're shifting your function in time, and you end up with the same result for every value of t. And that's the definition of a periodic signal. So you've seen this with the definition for like a sine wave. Sine of theta equals sine of theta plus 2 pi. Those values will be equal for every single value of theta. And that's the definition of periodic. So in discrete time, it's the exact same thing. You have a signal x of n, and you want to apply some arbitrary addition to your variable n, such as big N, and you spit out the same result. That's a periodic signal. And this is true for all values of t and n. So we're given a signal in this problem, x of t equals 5 sine 3t plus 1. So the way we want to determine if this is periodic or not, well, first off, this is a sinusoid. So we know by definition all sinusoids are periodic. And this one's just simply multiplied by some magnitude, 5, and it has angular frequency, a modified angular frequency, and a phase shift. So none of those things make it non-periodic. So using the formal definition, if I applied that to this specific signal, I would write 5 sine 3 times the quantity t plus big T plus 1. And that's going to equal the exact same thing that we had originally. It was 5 sine 3t plus 1. But if we've determined that it's periodic, through intuition or whatever other means, we want to then verify it by finding the period or finding the actual frequency. So the equation or the formula for a period is T naught equals 2 pi over omega naught. So you just plug and chug your numbers, where 3 is your omega naught. So 2 pi over 3 is your period, and that's what I've written here. So let's do that again with a discrete time signal. So we have x of n equals cosine pi over 4 times n. formal definition, we're just going to apply that, that shift to the n value, and it should spit out the same result if you plugged it into a calculator. And it does, because we know this is a cosine, another periodic function. But again, we want to, if we've determined through intuition that this is a periodic function, let's go ahead and find the period then. And so we have, for discrete time, the definition, or the formula for finding the period is right here. So n naught over m equals 2 pi over omega naught. Again, omega naught is just in front of the variable n. So our omega naught here is pi over 4. So just plug and chug, we have 2 pi over omega naught. And, simplifying that becomes 8. And for discrete time, you can say that this signal is periodic if your period is rational. And that's straight from the textbook and straight from the chapter 1 key concept sheet. And the reason for this, it has to be rational, is due to a concept called aliasing, which you guys will learn later in the semester. I think in the 5th week or 4th week, something like that. But yes, it has to be rational. I would explain aliasing right now, but I don't want to jump ahead if we're going to be learning it later in the semester. One other note for this problem is the fundamental period, as opposed to just a period, in both continuous time and discrete time simply means that there's the lowest value of k. And you're probably wondering where's this value of k? Well, up here when I gave you the definitions for, or the formulas for period and the formulas for period down here for discrete time, I assumed that k was equal to 0, and that would give me the fundamental period, as opposed to some other period. Because I can have any multiple of a period, and I can still call that a period as well, right? So if I have a normal sine wave, sine of x, and you have, let's say for whatever system I'm building, I'm going to call 2 cycles 1 period, and it makes sense for, whatever engineering thing I'm doing at that moment. That is a multiple of the fundamental period. And so when we're defining periods, we want to add this scaling factor, this multiple, because this number can only be a whole integer, a whole number. We want to add that. But if we're talking about fundamental periods, k is going to be equal to 1. And so I've made that assumption up here. But anyway, so that's the little note there for what a fundamental period is, as opposed to just a regular period. And so that's it for problem 2. So James will take it here to problem 3, and then we'll go from there. Thanks a lot, guys.
All right, problem 3. This is the system properties problem that I had to review quite a bit yesterday. This is we're given a function, x or y to the n equals x to the negative n plus 3, and we're asked to determine whether the system is memoryless, time invariant, linear, causal, stable. In each case, we write down the definition to properly justify our answer. So I'm still presenting Woody. Let me change it over to me. Nope. Stop presenting. Trying to figure, I'm having technical difficulties. Present to everybody. Stop. All right, trying to get to me here. There we go. Screen share. There we are. All right, back to number 3. So we're asked to consider the discrete time input of x of n, corresponding output signal y of n equals x to the negative n plus 3, and determine whether the system is memoryless, time invariant, linear, causal, stable. In each case, we're supposed to write down the definition to justify our answers. So the first one we want to look at is it memoryless? Well, let's just say we put the input in of n equals 2. We can see that y of 2 is equal to x of n to the negative n at time, or y of time 2 is equal to x of time negative 2 plus 3. So therefore, we can see that the output clearly depends on the past, and that we must have some sort of memory, and it is not memoryless. The next asks us if it's time invariant. So this one I described poorly, but now I think I've got it pretty good. Let's pick an arbitrary input. Let's say x1 of n, and we'll pick its time-shifted complement x2 of n, and we'll set x2 of n equal to the time shift of x1 of n. So what we want to see is if when we plug both x2 of n and x1 of n into the equation to get y2 of n and y1 of n respectively, if our y2 of n equals the time shifted of y1 of n, the time shifted y1 of n. So we plug in y1 of n or y2 of n first with the equivalent statement of x2 of n. So we take from this equation, we've taken this right here and plugged it into here to come up with this equation. And then we factor out the negatives, and we get y2 of n is equal to x1 of negative n plus n0, or n naught, plus 3. So if we were at our original y1 of n, we're to time shift that y1 of n, then we can see that just putting the time shift in does not give us the same, because now we're negative n minus n naught instead of plus n naught. So these two are not the same, and therefore we are time invariant, or we are not time invariant, or we are time variable. For the next is linearity. So we have two inputs. We have x1 of n and x2 of n, and then we have a third input, x3 of n, which is the combination of x1 of n plus x2 of n. So what we're trying to see here is if y1 of n plus y2 of n equals y3 of n, which corresponds to the x1 of n is the output of, when you plug x1 of n, you get y1 of n out. When you plug x2 of n in, you get y2 of n out. When you plug x3 of n, you get y3 of n1 and out. And basically, we want to see if y1 of n plus y2 of n equals y3 of n. So we plug in, we find y1 of n plus y2 of n equals, this is the x1 of n and x2 of n put in. So we have a term out here to the side, the coefficients that give us 3a and 3b. These are just coefficients they're just coefficients. Linearity doesn't, I mean, it could be like, say, a equals 2 and b equals 3 is the same as, it's more of a linear algebra definition. For the most part, you don't have to worry about them. So for x3 of n, we plug in x3 of n, which is equal to x1 of n plus x2 of n, but then we only have the 3 because we don't have each input added to the 3. So that proves that we are not linear. Causal, the output can depend on, means the output cannot depend on future events. And for any time our n is negative, let's say -2, our output will depend on the future. Therefore, we are not causal. Stable. Now, this is a hard to describe with the example they're given, because you're not given a function. You're just given some arbitrary x to the minus n. You really don't know. So the key actually makes the statement, if the input is bounded, then the output is bounded and stable. That's not a really good way to describe this stability, in my opinion, because it makes the qualification that first the input has to be bounded, which we don't know, we can't tell. So I set up a couple examples. Let's say we have x of n equals 1/2 to the n times the function, the step function at 0. So is this bounded? Well, we can make it, just look at the series of x 1/2 to the n times u of n. The u of n will remove all our negative values for us in our summation. And then we have this fancy geometric series that we have an equation for, gives us a number so that we know that this is bounded. One of the requirements on that geometric series is that this value has to be less than 1 and greater than 0. Next question, x of 3 or x of n times 3 to the n times u to the negative n, is that bounded? Well, let's look at, so we have 3 to the n. Now this one will remove all our negative values, so we're left with the summation of 0 to negative infinity of 3 to the n. So since how we know that all our n's will be negative, we can swap the 3 to 1/3 and swap the limits from 0 to positive infinity, and we still have our geometric series that is bounded. So I mean that's the best way to describe bounded. You're looking for something that goes to a number, does not feedback on itself and blow up or go crazy. With that, I will turn it back over to Woody.
All right, let's see. Looks like we're starting with problem 4 now. So let me pop up over here and read the question problem 4. So this looks like our first problem that deals with convolution, which is a concept from week 2. Convolution, problem 4, question asks us the impulse response of an LTI system is given by a system response, h of t equals e to the negative 2t times the unit step function. What is the output y of t when the input is x of t equals u of t minus u of t minus 2? In other words, this is just a pulse, and we want to see what happens when it goes through this system. So let me go over to my notes. So first off, we have an LTI system that just means linear time invariant. In other words, it means a system that we can build in real life. So I have here that our system response, h of t equals e to the negative 2t times the unit step. And I'd like to make a note that this is not, yesterday I was referring to this as a signal. This is not a signal. This is a system. This is a machine, let's call it, or a circuit or something like that. And this is how we characterize that machine when it's given signals. So this is a decaying exponential. And this unit step just says that we decay any input signals when we first turn the system on, as opposed to in the future. This just means that this system can be built in the real world. But this decaying exponential, if we were to give this, if we were going to give it, sorry, tripping over my words. If we were to say that this was a system in the real world, we could maybe say that this is a transmission line where a signal is propagating down it and it gets attenuated as it propagates down. So that's just an example of what the system could be. Now our input, x of t equals u of t times u of t minus 2. This right here is the unit step, and we modify this unit step by subtracting a delayed version of it. And so our end result is this is just a single pulse. Think of like a Morse code operator. If our system is a transmission line that goes from one end of the country to another, this is just a tap on the Morse code machine. So anyways, our question is, what is the output given these circumstances? So the first thing I did was I wanted to visualize what we're working with. So this is our input, x of t. And as you can see, it's just a unit step modified by a delayed unit step subtracted from it. And so it just becomes a pulse. And then this is just a decreasing exponential that starts at 0. And that's what the u of t is doing. It's just saying it starts at 0 as opposed to, this going off into the negative values like this. And what do we do when we convolute these two? So I know it's a little tricky to visualize what convolution is, and there are some explanations in the textbook and in the resources that the professor gave us. And on the best ones, I think, are on the Wikipedia page for convolution. It has some cool GIFs or GIFs, and it'll show you what convolution is actually doing in the time domain. Remember, this whole first half of the class, we're talking about signals in the time domain. But we know that we can convert or transform any of these signals or system characteristics into the frequency domain, which you've seen that with the Laplacian operator and differentials, or maybe linear algebra class. And we're going to be doing that again in this class as well later in the semester after the midterm. But in simple terms, who cares what convolution does visually in the time domain? It's overly complicated. And if you're interested, absolutely go to the Wikipedia page and look at those GIFs. But the takeaway that we'll learn later is that convolution, when you convert these to the frequency domain, so we would have x of j omega times h of j omega. That would be big X and big H, by the way. Those are the frequency domain expressions for the exact same thing. Convolution is simply the product of h of j omega times x of j omega. And then you can, a little bit more easily visualize what that's actually doing. And you'll see that again later. But let's actually go ahead and solve this problem now. So here I've written the definition of convolution, which you can get from the textbook or the key concept sheet. And it's simply y of t equals the convolution of x of t with h of t. And the way we do that is with this equation here. The integral from negative infinity to infinity of x of tau times h of tau t minus tau d tau. And we have this weird variable change where we took tau instead of t, and that's so that we can do this shift here. So this is equivalent to, if you've read the geographic or the geometric explanation of what this is doing, this is inverting your h of t about the y-axis. And so that's all we do, that's all we're doing there, and that requires this variable change. So let's go ahead and actually solve this now. So the first thing I did was I just rewrote what I'm doing. I want to do the convolution of those two things, and then I rewrote it using the definition. Now I'm going to actually get into solving it. So I put my x of t here, and that's just the pulse, and I replaced t's with taus, and then I put h of t here, and I just added this t minus tau instead of a t here. So you just plug them in, and then we want to go ahead and plug and chug essentially and solve these integrals. So the first step is I have a quantity multiplied by two terms here, and so I want to simplify that and basically expand this this multiplication out. And so that's what I did here. I split and simplified. So this ends up being two integrals, since this quantity gets multiplied with this term and this quantity gets multiplied with this term. So that becomes two integrals, and that's what I've written here. Here's the first integral, and here's the second integral. And this minus sign comes from this minus sign right here. Now the next step is we want to adjust our limits of integration from the unit steps. You can see that we have a lot of unit steps in both these integrations, and they will modify our limits of integration to not be infinity anymore. That way we can go with a definite integral instead of just a regular non-definite integral. So just to remind ourselves what these unit steps are. So this unit step is just the normal unit step, that the original definition of a unit step, where essentially you turn on a pulse at time equals 0 and it stays on to infinity. And then this one, this delayed unit step, is delayed by 2, so it looks like this. And then same thing with this one over here. It's also a delayed unit step, but instead of it being delayed by a specific amount like it is over here, it's delayed by this arbitrary tau amount. And so I've drawn that here as well. And that's just a reminder of what these unit steps are. So how do we turn them into limits of integration? Well, we know that part of the signal turns on as t equals 0. So we know we can set our first time point, our t1, if you want to call it that, equal to 0. And then our second point is going to be when you have this unit step modify this one. Remember, our original signal, we have just a pulse. So we have this unit step modifying this one to produce this single pulse. So that's what I've done here. And then we're going to do the same thing with the second integral using its respective unit steps as well. So let me scroll up. We have one unit step here starting at t equals 2, and then the second one starting at some arbitrary value of t, just like that. And then we're going to go ahead and integrate. So first, I did write this a little too early, I suppose. Before we actually integrate, we want to simplify this a little bit more. So I have here, we're going to use the exponent rules to simplify the integrands, specifically the product rule for the exponents. So in generic terms, if we have some number a to the m times a to the n, that will equal a to the m plus n. So we can actually use this and go backwards. So our integration has this, m plus n, where t is m and tau is n. and we can actually split that up into this. And what that allows us to do is, since our constant of integration is tau and not t, that means that t is treated as a constant, and it can be removed from, it can be put in front of the integrand symbol. So let's go ahead and do that. And here I've shown that. So if our expression is e to the minus t quantity t minus tau, well, first let me distribute this -2. So that's what I've done here. And then I'm going to turn it into my two numbers here using this product rule. So stick that back in front of my integration symbols. And I have this distributing the -2 and then turning it into this. I can then take the one that is treated as a constant, which is this one, and stick it in front of the integral symbol. Now what we have to actually integrate is much simpler, and it's just a single exponential, and everybody should know how to take the integral of that. Now we're going to do this for both integrals, so remember this when we get to the second integral. So plugging and chugging, I have some number that we can treat as a constant in front of my integrand, and then some simple integration. So taking that integration through, it equals this, and we want to evaluate at these 2 points, and then all that's multiplied by this, this magnitude here. And then basically you just manipulate it. You get it into this form. See, I have my t is here plugged in there, and my 0 is plugged in here. And then just continue manipulation using algebra, and it comes out to an expression like this. Further simplification takes it to this, and then finally, this is the prettiest result. We have 1/2 times the quantity 1 minus e to the -2t. Now remember this for later, because this is the solution for the first integral of our full expression. Remember, there's 2 integrals. So now let's solve the second integral. So we have a second integral here, and we're going to do the exact same thing we did with the first integral. The only thing that's different is our limits of integration. That's literally the only difference. So let's speed through. I did the same thing using the product exponential rule, or exponent rule, and then that popped out in front. Then I solved the integral itself, and it came out to this. Evaluate at these 2 points, and then I plugged in my t and my 2, and then it comes out to this ugly thing. Further algebraic simplification turns it into these expressions, one at a time, until finally I get to this little pretty thing that you see on the midterm review sheet and the answer key. So we want to remember this for later too. So putting the final solution all together, we just developed a piecewise function. So let me scroll up to the original problem where I have my cool drawings. If you have reviewed the geometric explanation for all of these things, what a convolution is actually doing is you're taking some signal x of t, convoluting it with h of t, but you have to adjust h of t. You have to flip it about the y-axis, and then you have a backwards version of it. And then you're going to move it forward until it finally touches your x of t at t equals 0. And then you're going to move through it, and the space that both functions share, you're going to keep track of the area that's under the shared space, and then plot that as a function as you move h of t forward. And it's a little hard to visualize that with my words and my little cursor here, but Wikipedia page on convolution shows it really well. And so if you can imagine this flipped about the y-axis and moved forward, we're going to develop a piecewise function where it's 0 for every point where h of t is over here not touching x of t at all. And then as we move it forward and we finally touch x of t for the first time at t equals 0, we then start developing an output that is a non-zero value. And then we move forward, and then it'll be developing some function. It'll be going up at a steady rate probably. And then once the leading edge of h of t hits the lagging edge of x of t, we then start decreasing our shared area under the curves until the point where h of t no longer is really touching x of t at all. Now, obviously, this goes on to infinity, but it gets pretty close to 0. So you can just kind of call it and say that it goes off to infinity. So anyways, that's the idea that we developed a piecewise function. So if we go down here, your math shows the piecewise function. And so before that flipped version of h of t even touches x of t, and they have no shared area, no shared space, you have a 0 output. And so that's for all t less than 0. In other words, before we even turn the system on, we should have no output. That's the intuition there. Then when they first touch each other, you get this function. And that's only for when they're when the leading edge of the h of t function is inside the x of t function. And that's between 0 and 2. 0 and 2. And that's what this this is here. And then finally, the h of t will move on past t of 2 with this expression here, and that's the full expression. And we just got that from our 2 integrations that we did earlier. So that's problem 4 in a nutshell, and hopefully I did a pretty good job explaining it. If not, feel free to ask some questions in Piazza or the YouTube channel, and we can take it from there. So from here, James is going to take it back with problem 5.
Hello, everyone. Welcome back to me, present to everyone. All right, so problem 5. Anyway, convolution is a convolution problem. It's a direct or discrete time convolution problem. It asks us to consider the following interconnection of an LTI system. That means it's a linear, it's time invariant. Here we have h1 of n equal, we have the equation for h1 of n, which is equal to the unit step, and then from 0, and then it turns off at when n equals 2. And h2 of n.
I think it's still displaying my screen. I'm sorry.
Am I?
The YouTube channel still shows my screen and not yours.
Okay. I see it move when I scroll. Okay, now we're good. Sorry. The little green. Swapping presenters gets to be difficult sometimes, this thing.
Also, I was wondering if you were able to zoom in so that it shows bigger on the YouTube channel.
Oh, I can. Oh, no, zoom in here. That should help out. All right, convolution. Consider the following interconnection of the LTI system. So we have h1 of n, h2 of n, and what's the impulse response of the overall system? We look at our drawing. H1 of n feeds right into h2 of n, so our overall system response is h1 of n convoluted with h2 of n. So I've done these 2 ways, both graphically and math. So for a graphical system, I just drew out h1 of n and h2 of n. I'm sorry I didn't put these at the like the zeros are swapped a little bit on the paper. But so method 1, we took the h1 of n and just swapped all the n's for k's and put it on the k-axis. And for h2 of n, we put h2 of n minus k. So a lot of people may not understand how you get to the n minus 1 here for your value of k. So we have the leading edge of this is u of n minus k plus 1. So we solve that for k, and that should be a plus, right? Pretty sure I wrote it down wrong on my paper. Let me see the key real fast. It is a, yeah, that's an n plus 1. I got it down here as n plus 1 and just wrote it down wrong there. Sorry, it's a little, I'll fix that up before I upload this for Piazza for you guys to look at. N plus 1, we'll look at the different time scales. We have n plus 1 for, this is when n plus 1, this leading edge is less than 0. So that's your k value. So n plus 1 plus k less than 0. You're over here. And this is the h1 of n. This is h2 of n. So there's no intersection. So the answer is 0. When n plus 1 equals 0, you've moved this n plus 1 right here. So we have an intersection between h1, the first term of h2 of n, and the first term, the trailing term of the h1 of n. So we have 1 overlap. So our answer is equal to 1. Now that n plus 2 equals 1, or n plus 1 equals 1, we are completely overlapped. So our output is 2. And when n plus 1 equals 2, so we moved n plus 1 over here. So now we have the tailing edge and the leading edge overlap. So the output's 1. And then if plus 1 is greater than 2, we've now moved it all the way across, and we are no longer overlapping. So we gather up these terms. We get n plus 1 is for the n plus 1 less than 0. So this is your k. This is n plus 1 and k. So you could have any variable of n in there. But anyway, if that k, if this term is less than this k term of 0, then your output is 0. If your k term, this is basically a gathering up of this series of graphs. So then we look at this and we can make this a set of delta functions to make a nice, pretty equation. So to make the delta functions, we look at the different points when n, and we want to basically put this back in terms of n. So we know our k is equal to 0, our k is equal to 1, our k is equal to 2. So that happens when n equals 0, when n equals -1, and when n equals 2. Or no, when n equals -1, n equals 0, n equals 1. This should be 1 right here, not -1. I'm sorry. So that gives us our terms to go into the delta functions. And these should be delta functions there. So anyway, we know we want our n when n equals 0, or when n equals -1, this one is active. When n equals 0, this one is active because we have a 2. When n equals 1, this one is active. The alternately and much, much easier way is any discrete time really can be expressed in a set of depending on how long you want. Especially if it's a unit step function, you can convert those into a delta function and just make your life so much easier. So here h1 of n is converted to the delta function where you only have 1 at 0 and 1 at 1. h2 of n is converted to the delta function for when you have 1 at -1 and 1 at 0. And when you convolute those, you're just adding the delta functions together, and you get this nice you get the same answer without a page of notes. So the next part B, that asks us to convolute our total system response, h of n, with this input signal, x of n. So x of n is equal to a to the n times the step function u of n. What does the restriction, and also it's given the additional restriction that a is less than 1 but greater than 0. So what does this restriction mean? It means it will be an exponentially decaying function. So we can look at this, and it just kind of goes off. It also means it is bounded, incidentally, but for the graph purposes, it's nice to be able to see the graph. So we know that this is 1 because a to the 0 is 1. And this is a because a to the 1 is a. And then this is these decay off exponentially. So we do our substitution where we have k and n minus k. So we flip those around, and we get at the bottom, you can't see it, or here's n plus 1. So this is our n plus 1 term that we're going to follow along. So for when n plus 1 is less than 0, there's no overlap. When n plus 1 is greater than 0, we have an overlap of 1. When n plus 1 is equal to 1, we have an overlap of 2. And this is a. Like, how do I know it was a? Because n to the 1 is at 1, so n equals 1. Therefore, a is a. So actually, this should be because it's k equals 1, not n. So we know it's a to the first. Anyway, it's a 1 times a. For n greater than 1, we have a complete overlap as it comes through. and it will continue to overlap into infinity. So we have to create an equation. So we know that this term here is a to the k times h n minus k. This term here is a to the n minus 1. That should be k. Hi, Brad. So a to the n minus 1 times h of 1. Oh, wait, sorry. This is the general term. A to the k times h to the n minus k. So for this one is a to the n minus 1, which would be 0 in this case, times h of 1. A to the n plus 1 times h of 0. A to the n plus 1. N. This should be a to the n, not a to the n plus 1. So a to the n times h of 0, a to the n. Anyways, we know our values of h of 0, 1, and negative 1 because they're 1, 2, and 1 from the function. And we get this nice, this collects all our terms. So this is for when n is greater than 1, or n plus 1 is greater than 1, so when n is greater than 2. Or 2 or greater. So the alternate method with math, we have our, again, we use the sampling function or the sifting property. So we have x of n convoluted with all these, so we just have x of n times these. So we get the sifting of, so we get x to the n plus 1. So you basically take the argument of the delta function and plug it into the x of the n plus x of n function. So we have x of n plus 1, and then we have 2x of n, and x of n minus 1, plugging in x of n equal to a to the n. So we get it's a to the n plus 1 there, 2a to the n, so that's the n, and then a to the n minus 1, which was the same thing we got up here, just reversed. So we gather all our answers up to get a piecewise full answer. So if n is less than negative 1, we get 0. If n is equal to negative 1, we get a 1 out. If n is greater than equal to 0, we get 2a. And if n is greater than 0, we get this function here. So that's probably clear as mud. But it said the math way is generally easier, especially if you convert it to a delta function. If you're getting delta functions in there, you're going to have a good time. The graph is, you can see it and kind of intuitive, and you can get an idea if you're right or not, but then getting the function out of the graph can be a challenge. So if there's any questions, I will turn it back over to Woody.
Okay, and let's make sure my screen's displaying. Sweet. Okay, so we're going to get into problem 6. This is another systems properties problem. So we're going to take a look at 2 signals, one in discrete time and one in continuous time, and we want to ask ourselves the question: are these signals, or are these systems rather, causal and stable? So for continuous time and discrete time LTI system to be causal or stable, what is the requirement on the impulse response h of t and h of n? The followings are the impulse response of the LTI systems. Determine whether each system is causal or stable. And just as a reminder, when we have the notation h of n or h of t, that's referring to a system, not a signal. So a system is something like a machine or a circuit or something like that. And then you give this machine an input. And the inputs we usually call x of t. The output's y of t. So anyways, I just want to make that distinction. But let's get into our definitions for causal and stable. So let me go over to my notes. And I've written the straight from the, I think it's the textbook or the chapter 1 key concepts. Here, the definition for causality is in continuous time, we have that h of t, the system, is 0 for all t less than 0. In other words, before we even turn the system on, we should have no output. And that makes intuitive sense. And that's causality. Same with a discrete time system. Before we even turn the system on, for all values of n less than 0, our system should output nothing. So that's causality. Now the requirement for stability, a little bit more rigorous, mathematically speaking at least, but it's still a simple idea. So in continuous time, we have this integral, and in discrete time, we have this summation. Remember that an integral is just a summation over infinitesimal points. Anyways, for stability, in a very generic, intuitive sense, a system is stable if you're given the system a bounded input, it should produce a bounded output. In other words, an example of an unstable system would be putting a microphone up to a speaker, and the microphone will then take the noise that's coming out of the speaker and amplify it, send it over to the speakers. The speakers will then output it even louder, and then continue that cycle ad infinitum until the speakers blow. So that's an unstable system. You are giving it an unbounded input. As the speakers get louder and louder and louder, the microphone is going to take that louder and louder signal and then amplify it over and over again. So that's an unstable system. And we don't like unstable systems, because that's how you waste money on burning out circuits and blowing up speakers and stuff. So the mathematical definition for stability, though, is in continuous time, we want to look at the system, look at the magnitude of the system over the entire curve, the entire plot from -infinity to infinity, and we want to see if that produces an output that is bounded, that is less than infinity. And so that's all that means. Same thing with the discrete time. We want to take the magnitude of our system, the function that characterizes our system. We want to look at every point from -infinity to infinity, and we want to make sure that this thing is bounded and it doesn't equal infinity anywhere. And that's how you produce a stable system. So definitions are cool and all, but let's actually look at a real problem and determine if it's bounded or not, and if it's causal or not. So we are given two signals. In part A, we're given this discrete time signal, h of n, equals 0.9 to the n times delayed unit step function. And I say delayed, but this is delayed to the future. So projected in the future? I don't know. This system is impossible in real life, and I've already kind of given away the answer by saying that. But any system that relies on an input from the future is not causal. It's impossible. We would not be able to implement this in real life because we don't have time machines in the real life, in the real world. They are forbidden. So this right here is really what makes it not causal. And if you plot this into a picture, it makes more sense. So we can see if we call the origin, the y-axis, we call that the present, and we call the positive values of this x-axis, or really it's an n-axis, I guess. These positive values are the past, then we would say that the negative values are the future. And since this graph goes into the future, it is no longer causal. In other words, since h of n has a non-zero value at t less than 0, I wrote t here, but it's supposed to be an n because this is a discrete time, this system is not causal. So that one's pretty straightforward. Now, for this same signal, what about stability? Is it stable? Because you can have stable signals that are non-causal. You'd only be able to simulate them in a computer or something, but you wouldn't be able to build it in real life. But you can still make it a stable system. So let's look at the definition for stability right here. We want this whole thing, the magnitude, I forgot my absolute value bars here, but the magnitude of it to be less than infinity. So plugging in our actual signal, 0.9k to the k times the unit, a delayed unit step function, then we want to evaluate k equals -infinity to infinity. Well, the first thing I want to do is do something with this unit step function. It's actually going to modify our summation values. So since the unit step function is 0 for every value before -1, as shown here, we can actually modify this k value to basically get rid of all these values that it's zeros, because 0 times anything is 0. So we do that. Since this is shifted to n equals -1, we can then say that k equals -1, and then only evaluate from there up to infinity. And then infinity comes from this going off to infinity. So that simplifies that, because now we just have this expression, 0.9 to the k. So the next thing I want to do is turn this summation into something that we've seen before, such as a geometric series. So we learned geometric series in Calc 2. and we restated them here in our textbook and in the chapter 1 notes. We have these 2 geometric series that we deal with in this class. There are a lot more geometric series, but luckily we don't have to deal with any of the other ones because they get a little bit more complicated. But anyways, we want to turn our problem into one of these. Since we're dealing with a problem where we have some k value going to infinity, we're going to use this geometric series. So let me go back to my notes, and that's what I've written here. So we're going to use this. We want to turn this into a form that looks like this. So the only thing we have to do that is do something with this here. Since this is a summation, we have a bunch of terms going from -1 to infinity. Well, I can just already evaluate this first term and then just use the geometric series to evaluate the rest of the terms. And that's what I've done here. So evaluates to a number. So if I plug in k equals -1, k equals -1, k equals -1, this is just a number. 0.9 to the -1 power, I think I calculated that yesterday on the calculator, was 1.1111 infinity. It's just a number. And that's just one term over this infinite series, or this infinite sum. Now, how do we deal with the rest of them from k equals 0 to infinity? Well, that's what the geometric series is for. So we can now put this into this form that we recognize as a geometric series from k equals 0 to infinity. Remember that we've already evaluated k equals -1 right here. And then what does this equal? Well, it equals this thing. So 1 over quantity 1 minus a, 1 minus alpha, where alpha is 0.9. So putting that all together, I have that here. 0.9 to the -1 power plus 1 over quantity 1 minus 0.9. And putting this into a calculator gets this number. And we can see that this number is a number and it's not infinity. So this system is stable. And that's for the first signals, part A. So let's do this again with another signal and see what it does. So part B, we're given this signal. And again, we have a unit step function times some exponential or some, whatever else function. So this is e to the -3t is an exponential, a decaying exponential. And we have, again, we have a unit step function, but this time, instead of it being delayed, it is reversed. It's also delayed too, but so the first thing I did was I drew a picture of that unit step function, and this is what it looks like. So we have this negative sign makes it go backwards, and this value of 1 makes it start at this value of 1. And we're asking ourselves if this system is causal or not. Since h of d has non-zero values for lots and lots of t less than zeros, again, this is a t because this is a continuous time signal, so I am using t correctly instead of n. This system is not causal because we have lots and lots of values that are less than 0. Now, what about stability? Well, putting in the definition of stability, where I did remember my absolute value bars this time, again, I took my unit step and I adjusted the limits of integration like so, where this negative infinity comes from this negative sign here, and this 1 comes from this 1 here. It's more easy to see here and here. So these are the new limits of integration, and we just have a integration of a simple exponential function. And so that just becomes the -1/3 times the exponential evaluated at these 2 points. And plugging and chugging, I have my 1 here and my negative infinity here. And whatever these numbers turn out to be, minus something that turns into infinity, becomes infinity. And I say infinity, but this is a negative infinity. But remember, our definition includes these absolute value bars, so we're just looking at the magnitude. So this thing is evaluated to infinity. Therefore, this system is not stable. So hopefully that makes sense, and that's problem 6 in a nutshell. And we're going to go on to problem 7 with James.
Sorry, I saw Colby ask the question on YouTube. I'm just typing up some answers real quick. He was asking about power. Maybe we'll work an example or something after we do 7, or after we finish off as part of the. After we get through this portion, we'll answer questions and maybe possibly work an example for them or something. So question 7. Am I presenting? I am. 7 asks us, compute the Fourier series coefficients of the periodic signals x of t equals 1 plus cosine of t times 2 sine of t, or sine of 2t. So general side right here, for general argument for sine or cosine function. This t can be thought of as k omega t, which is a horribly written k. But we need to find an omega naught for which the value of omega to work with all the functions. So these two equations, these will, if you don't know these, they'll become your life in this class and other classes. I was taking a midterm last Thursday and I was using omega equals 2 pi f or omega equals 2 pi divided by period. These just know them by heart in general. So we can go from omega to omega naught k, and that's how we to change our argument, so we can get a fundamental angular frequency that works with all our sines and cosines sine and cosine functions that are multiplied together. So our fundamental period is 2. So this comes from, so we're looking at the sine function. So we're pulling this 2 out, and we're looking at the period, which is 1 over the frequency. So this is omega, basically. So we solved the equation omega equals 2 pi f, or 2 pi divided by period. We solved that for period, and we got 2 pi divided by the angular frequency is equal to just pi. For the cosine function, we pulled down the 1. You can just think there's a 1 there. And then our period is 2 pi divided by omega, which is 1, which equals 2 pi. So for both, the period that works in both cosine and sine, our period naught, our fundamental period is 2 pi, because it's you can't have a period of pi with the cosine t, because then you'd only be halfway through the function before it started repeating itself again. So we need to use a period of 2 pi for it to work. That we're using that, we can calculate our fundamental frequency, fundamental angular frequency. We're using, again, 2 pi divided by period. So we have 2 pi divided by 2 pi, which equals 1. So from here on out on these, I will use red to indicate omega naught, and k will be blue. I know sometimes they're just kind of not, like the ones aren't explicitly stated, so you get confused as to where they get lost at. So I wanted to put them in here so you can see them and see what's going on. So we've changed our function with our omega naughts in our case to represent what we need to see. We have 1 plus a cosine of omega naught of 1, or a k of 1 and omega naught of 1, and a sine of an omega naught of 1 and a k of 2t. So we're going to use our Euler's general equations. These are the general equations for Euler's, where cosine of omega naught t equals e to the j k omega naught t plus e to the negative j k omega naught t divided by 2. Sine times k omega naught t equals e to the j k omega naught t minus e to the negative j k omega naught t divided by 2j. So we've taken this function here and plugged it into this transform to get us into this equation here. So we have e to the j times 1, so that's omega naught and k, t plus e to the, we know what our value of k and omega naught are. And then down here I've separated the denominators because they're over a common denominator, so you just put them over their own denominator. Now you can't do that with numerators. I mean, sometimes I've had a brain fart and gone, oh, I just separate the No, you can't do that with numerators. Numerators, you'll have to do something called partial fraction expansion, which, believe me, you'll learn about that later. But for the denominators, you can just split them because they're a common denominator. So from this, we FOIL these out. So I left this one in its form, but I kind of combined these two. So for our first term, we have e to the jt times e to the j2t divided by 2, or times 2 times 2j. So just combine our numerators and our denominators, which gives us 4j on the top, and then e to the 2j times e to the j2t And we did this down the line. Pay attention to the coefficients because we have a minus here. So we'll have a first one, we'll have a plus. Inside, we'll have a plus. Outside, we'll have a minus. And last, we'll have a minus as well. I didn't do them in a FOIL order. I just did the process. So anyway, properties of exponents. Whenever we have e to the jt times e to the negative 2jt or any of these exponents, we could just add our exponents with our like. So we just combine our like terms, and that's what this little area is representing. So we've got the 4j's all combined. Then we have e to the jt plus e to the 2jt, and jt minus j2t. So jt plus jt is j3t right here. Jt minus 2t, j2t is negative jt. Negative jt plus j2t is positive jt, and negative jt minus 2jt is negative 3jt. So that's where these all came from. And now we know that the omega naught is 1. So that we know that k is just these coefficients. So omega naught was 1 from way back up here. So the only thing, the coefficients on the exponents have to be k. So now we plug those in. We know we have our A3 term. Hi, Virginia.
Hi, Dollar.
I'm going to mute you. Oops. I don't know how to mute you. There we go. So, sorry about that. So we know that omega naught is 1, and so that we have these coefficients to be our k's. So we have our A3 coefficient is 1, is this one. So we just pull this coefficient out, which is 1 divided by 4j. Our negative, or when k equals -1, our coefficient is negative, because it's negative right here, -1 divided by 4j. Our A1 coefficient, our first k equals 1 term is 1 divided by 4j. It's a positive, so it's 1 divided by 4j. And our -3 term, or k equals -3 term, is -1 divided by 4j. And of course, our 0 term is this DC, this constant out here for 1. And that's pretty much 10. So that, I mean, it's the cool thing about this is it lets us do convolution, which 9 and 8 and 9 touch on them a lot more, but it lets us do convolution without having to do convolution integrals. So that's it for 7. I mean, any questions? Anybody has any questions on 7? I think the YouTube channel is back farther. So anyway, I will turn back over to Woody.
Okay, we're going to get into problem 8 now. And this one, again, talks about Fourier series. And this question is split into 3 parts. So we're going to start with part A, and then we'll get to part B and part C later. So first, the question for part A is, what are the Fourier series coefficients of the periodic signal x of n equals sine of 2 pi over 6 times n plus pi over 4 with a period of n equals 6. So some things to point out: we are just dealing with a discrete time signal. We have a periodic signal, which we already know because we're in the part of the semester where we only learn about periodic signals. We have an angular frequency of 2 pi over 6, and we have a phase shift. Now, before I actually start solving this, I'd like to note, if this was pi over 2, this would greatly simplify our expression here. If it happened to be pi over 2, using the trigonometric identities, we could have turned this into a cosine, and then it would just have this value here, and we wouldn't have to worry about phase shifts. But we're not lucky here, and this is not pi over 2, it's pi over 4. So we're going to have to drudge through this a little bit. It's going to be a little bit more complicated, but we'll get through it. So let's go to my notes, and we'll attack it. So the first thing I've done is I've just reiterated what the problem gave us. That's our signal. We have a period of n equals 6, and we want to know what the Fourier series coefficients are. So the first thing I do is I verify the period. This isn't necessary, but it's good practice. So this is the expression for discrete time. Remember, discrete time, we want a rational expression, and that's why we have this n over m. And if we're talking about a fundamental period, this m should be 1. So I'm just going to plug in our angular frequency into our expression. So 2 pi over 2 pi over 6, just plug and chug, and then it comes out to 6. And lo and behold, we just verified our period here. Now let's solve the problem for the Fourier series coefficients. The first step to do that is use Euler's identity to convert the sinusoids into complex exponentials, usually a summation of complex exponentials. So here I've written Euler's identity for a sine function, a sinusoid, since we're dealing with sine and not cosine. And simply put, we just have the sine of tangent, or I'm sorry, sine of theta equals 1 over 2j times e to the j theta minus, the important thing with sine is that there's a minus here, minus e to the negative j theta again. Just for gee whiz, if you're interested, the reason why that there's a minus sign here, if you've noticed the Euler's identity for a cosine has a plus here. Now this is a minus for the sine because a sine function is asymmetric versus a cosine function is symmetric about the origin. And that's just gee whiz if you want to know where it comes from. Now we have a phase shift in our signal, and that's what this is. This is phase shift. It modifies our signal. It delays it a little bit. So what do we do with Euler's identity when there's a phase shift? Well, we can just lump it into this theta here, but I can expand this theta into omega. You can use whatever variables you want, but I used omega naught and phi. Phi is our phase shift. And so all you do is you take this entire expression and you stick it where the thetas were originally. So I've done that here, quantity omega plus phi and quantity omega plus phi. And they just go in these exact same spots that these thetas were before. So knowing that we have a signal like this, we're going to do the exact same thing with Euler's identity. So I've just taken that entire quantity and put it into these parentheses here. And that's all you have to do. Well, right now. Now the next step is we want to simplify this. So we want to be able to split this out somehow. And the way we do that is, remember earlier I showed you the product rule for exponential, or for exponents. And maybe I can scroll up and find that again real quick. And just remind ourselves what the product rule for exponents are. If we have some arbitrary base a to the m power times a to the n power, that becomes a to the power m plus n. And we can use that, we can take this going backwards and split it. Now, if we have an integral, let's say, or in our case here, we have one of these as a value that, is a constant, and one of them is not a constant, it has some variable that depends on something. We can then split them up and make things easier. So let me scroll back down to where we were. Where was I? Product rule. So we want to turn this into, we want to get this out of this expression and simplify it. So I did that. And that's right here using the product rule for exponents. And again, right here for the other term. And now we can just put these in front over here and simplify them. So I've done that. I've taken this and taken it out here, which I've done here. And then for our second term, but this time we have this negative here. And that simplifies things because we want to look for things in terms of these, some multiple of these, right? Since our coefficients are part of the part in front of the term with the omega naught in it, we can say that there are two coefficients here. So what that means is our original signal was just a sinusoid, and we know that with Euler's identity, that gives us two exponential terms. That means we can say that there are two coefficients here. Because remember the definition for finding our AFKs. Are we dealing with the... Let's see, we're dealing with a discrete time signal, so we're going to use this definition of AFK. It's just a summation of all the discrete time points in a given period, in a single period. And that's what this means right here. This brackets with the n just means that we're going to only do the summation over one period. So let me go back to my notes. And if we're doing that summation over the whole period, and we only come out with two terms, where am I? We've only come out with two terms. That means we have two Fourier series coefficients. Now, what are those Fourier series coefficients? Well, they happen to be the magnitude in front of our two terms. So these are the two magnitudes, and this is the two terms that we get here. So anyways, our final result becomes a1 equals 1 over 2j, e to the j pi over 4, and then a minus 1 equals 1 over 2j, e to the negative j pi over 4. Now, you might be asking yourself, why did I choose a1 and a minus 1 instead of anything else like a2, a minus 2, a5, a minus 5, or anything else? And the reason for that is because our terms were in our expression here were in terms of our fundamental frequency, 2 pi over 6. Remember, that was given to us in the original problem. We know that the period is 6, and therefore the fundamental frequency, the angular frequency, was 2 pi over 6. We know this is fundamental because we calculated that here, fundamental. And therefore, our final expression being in terms of our fundamental frequency and not some multiple of it means that our k values were 1 and minus 1, as opposed to some other values. If our final expression here had, let's say, 4 pi over 6 or 6 pi over 6, which is just pi, then we would say that this was some multiple of our fundamental frequency, and we would call it, a of 2, a minus 2, depending on what the multiple is. So hopefully that makes sense. Now, let's do part B. So part B asks the Fourier series coefficients of a periodic signal y of n with period n equals 6 is a naught equals 1, a1 equals 2, and a minus 1 equals 2. What is the original signal y of n, the original output? So this is having us go backwards. This is giving us our series coefficients, and then it asks us to recreate the signal that they represent. And remember, a Fourier series is simply, it's a way of converting from your time domain to your frequency domain. And I think I've talked about this in Piazza a little bit, but since the first half of the semester we talk about periodic signals, we convert them to the frequency domain by, we call it a Fourier series instead of a Fourier transformation. Later in the semester we'll learn about aperiodic signals, which is non-periodic signals, arbitrary signals, and we'll get into Fourier transformations, which does the same thing. But anyways, so let's go back to my notes and see how we solve this. So part B, I've just restated what we're given. We're given these Fourier series coefficients, and we're given a period, and we want to know what the signal that they represented was. Now remember, if our input was periodic, our output will be periodic. And so that's what this is useful for. But to actually solve this, we want to take the definition for what a signal is. And a signal is simply the summation over a single period of our Fourier series coefficients times this weird complex exponential. And that's all you have to do. So this is a compacted form, but let's expand this sum real quick and just see what it looks like. So y of n expanded over a single period, whatever that period might be. Here our period is 6, so I should have done 6 terms, but I ran out of space and I got lazy, so I only did the first 3 terms. So our first 3 terms are a0 times e times this complex exponential evaluated at k equals 0. So k equals 0 is right here. K equals 0. Actually, that should be n equals 0. But anyways, don't mind that. And the next term will be a1 times this complex exponential evaluated at 1. And then a minus 1 times this complex exponential evaluated at minus 1, and so on and so forth, for however long your period is. And here I should have done 6 terms, but I got lazy. So since we're given 3 terms, we know that we only have a summation of 3 terms in this period of 6. So 3 of the terms in this period of 6 were 0, and 3 of them were non-zero values. So anyways, let's go ahead and determine omega naught. That's what I did first. And we use the discrete time formula for the relation between period and angular frequency, and we just plug and chug, manipulate it so they can figure out what a meganaught is. And it turns out that if our period is 6, we just plug that in here, we get 2 pi over 6. And so that we're going to use that. So now I want to expand this summation with the terms that were given using these. Remember, everything else, if it's not given an explicit value that's non-zero, it's going to be equal to 0. So if we look at this whole period, A2, which is not represented here, A2 equals 0. A minus 2 equals 0. A3, A minus 3, A4, A5, A6 all equal 0. So we don't have to worry about those terms. We only have to worry about these 3 terms. So that's what I've done down here, right here. So our original signal, here's our first coefficient, A0. Here's our second coefficient, A1. Here's our third coefficient, A minus 1. Because that's what we're given. Everything else is 0, so I can ignore them. Now, when I create these signals, this is where this omega naught comes in, because we have the sum times a term that has omega naught in it. So we plug those in too. We have a complex exponential with omega naught in it, which I didn't write omega naught here because it's multiplied by 0, but I did write it here. I did write it here, and then I went ahead and simplified this to make it prettier, and that's what I've written here. So this is prettier because this evaluates to 1, and so I have just 1 times 1 equals 1, and then I simplified this. I don't need to write this 1 explicitly, so it's written again here, and this minus 1, I just took the minus sign and put it in front. You can see I accidentally did it here, but I didn't want to show that yet. Anyways, this is a final solution. This is a final answer. I don't think you'll get docked points if you put your final answer in this form on the exam, but don't quote me because I'm not the grader and I'm not the professor. I'm just a TA. But if you want to continue this and put it into a pretty form like a sinusoid, because sinusoids are pretty, like sines and cosines, we can do further manipulations to put this into that form. That's what I've written here. But what if we want it in the form of a sinusoid? What do we do? Well, to do that, you're going to look for patterns. Remember Euler's identity. I chose a cosine. If we want to use a reference signal of cosine, the reason why I did that is because of this plus sign here. This plus sign here. If this was a minus sign, I would have used Euler's identity for a sine wave. But we don't. We have a plus. So I use cosine. So this right here is just the same thing of this rewritten. Since we have this plus, it looks like the Euler identity for cosine, and we have a plus here in front of the j, which you have that in Euler's identity, and you have a minus sign in front of the j, which we have that in the Euler's identity as well. So this whole thing, rather this part of it, sure looks like something that could be Euler's identity. We just have to manipulate it a little bit. So Euler's identity says that we have to have a magnitude of 1/2 and not 2. So how do we get these 2's into 1/2? Well, you might have learned in other math classes or whatever, the concept of a well-chosen 1. Well-chosen 1 is I want to multiply these things by 1, you know, like 2 over 2. That's equal to 1. But I want to turn this into a form that I recognize, such as Euler's identity. And that's the whole idea there. So this right here is your well-chosen 1. This was my original magnitude that was given by my initial solution. And now I have something in the form of Euler's identity. And this is cosine, because this is the same exact form. We have a 1/2. Here's the 1/2. We have a positive j here, positive j here. This is omega naught right here, 2 pi over 6. And this right here is a minus j. We have a minus j here, and this is omega naught again. So this right here is Euler's identity. It is a cosine. It is a cosine of this argument here. And remember, I had to create this 2 out of thin air using the well-chosen 1, so that gets multiplied by my original magnitude, 2. So this turns into 4 cosine 2 pi n over 6. Now I'm going to put this all together, because remember we had this other constant here from our original solution. Putting it all together, we get this final solution that is in a pretty form, that is not a series of complex exponentials, but is a sinusoid, a cosine. So we have 1 plus 4 cosine 2 pi n over 6. And that's how you do part B. So now let's get into part C. So let me go back over to here, and let's see what part C asks us. Part C says, what are the Fourier series coefficients of a periodic signal z of n? And we're given that z of n is basically a pulse train, a train of spikes with a period of n equals 2. So this is the direct delta function. Direct delta function, by definition, is just a single spike in discrete time. And that spike equals 1 at a discrete point in time. But this delta function, by the way, this is also called an impulse function, is modified. It's delayed. And it's delayed by a value of 2. So anyways, let me go back to my notes and I'll explain it further. So here I've just rewritten what the problem gave us, and it asks us to get the Fourier series coefficients for this. So first thing, I looked at the definition of a Fourier series coefficient. This is the Fourier series coefficient, and this is how you evaluate your Fourier series coefficient. So we just multiply the inverse of the period, which our period is 2, times the sum over a single period of our signal x of n that we're given. And here we call our signal z of n, but it's, we can call it x of n. It is x of n. It's just some signal. And then we multiply that by some complex exponential that has a value omega naught in it. Remember, omega naught is related to the period. So let's actually do it. Here I plugged in everything of note, of use. So we have our period of 2 here. We evaluated this over a summation over that period of 2. So in a period of 2, you only have 2 terms. So we have a value at n equals 0 and a value at n equals 1. So that's 2 terms. If we had 3 terms, this would be, n equals 0 to n equals 2, or yeah, n equals 2. And that would give you 3 points in discrete time. So the next thing you're wondering, I have a delta of n here, but our signal was delta of n minus 2k. I talked about this in Piazza the other day, and what this delta of n minus 2k is it's just a series of spikes that skip every two values. And I wish I drew it here, but if our signal is a delta function that over the k space from negative infinity to infinity, we have this expression that takes in k here. Sorry, I'm not explaining this very well. Let me back up. All right. The definition of a delta function, no matter what, is whenever the argument of the delta function, the argument being the thing that's inside the brackets, whenever the argument evaluates to 0, this delta function will output a value of 1. So how do I get this argument to become 0? Well, I just set this equal to 0. N minus 2k equals 0. So when will this be valid? When will this be true? Well, this will be true when our k and our n lines up at this rate, at this expression, to equal 0. So I'm going to look at all of the k values in all of infinity and find out when that equates to 0. So n minus 2k equals 0. Well, that becomes n equals 2k. And so basically every 2 values of k, n will become 0. And this whole expression becomes 0. And then it outputs as a 1. Hopefully that makes sense. And if it doesn't, you can read through my my post in Piazza, and hopefully it makes more sense there. But you're probably wondering, going back to this problem, our expression here evaluates the sum over a single period, where this is over many periods of this infinite space. So when I apply this definition to this problem, and I only look at a single period, this delta function only has a single spike in that one period. Because at n equals 0, n minus 2 times 0 is 0. So our delta function outputs as a 1. At n equals 1, however, it's a different story. If n equals 1, n minus 2k is no longer 0, and so this becomes a 0. And so I'm only going to put this into my expression and not this whole thing. Hopefully that makes sense. So anyways, we want to apply this. And this is just reiterating what I just said. And now we just want to plug through for all of our values of n that matter to us. And that happens to be only n equals 0, because n equals 1 gives us a 0 result. So I plug in n equals 0 into my n of the definition and evaluate this whole thing. So this becomes 1, and this becomes 1, because e to the 0 power, because whatever this times 0 is 0. So e to the 0 power becomes 1. So we have 1 times 1 times 1/2. And that equals 1/2. So we have a Fourier series coefficient a0 equals 1/2. And that is the final result. Now, another way to solve this, a second methodology, we could have just expanded the whole term too. I did this part in my head, and explaining it without showing it might be a little confusing for those of you who are watching me right now. But let's go ahead and just expand the whole thing, and you can see it outright. So I have a of k equals this magnitude that gets multiplied by everything, which is simply 1 over n, times each term that's in the period. So remember, if this period was more than 2, we would have more terms. But we only have 2 terms because the period is 2. If this was n equals 6, we would have 6 terms here, and I would have written 4 more terms here. But I don't. So we have this first term, n equals 0, times this complex exponential evaluated at n equals 0, and that becomes 1 times 1. And then the second term is delta evaluated at n equals 1. Well, a delta at anything that's not 0 is 0. And that's what I've written here. And since this is 0, who cares what this evaluates to? I don't care. Why should you care? Because whatever this number is times 0 just becomes 0. And so this term drops off, and we're only left with this term. And since 1 times 1 times 1/2, that equals 1/2. And remember, I chose this 0 here because this was 0 here. This was 0 here. All right, hopefully that makes sense. And that is part C of problem 8. So I'm all done here, and we're going to give it back to James here, and he's going to go on to problem 9.
Alrighty. So problem 9. Any questions about problem 8 or anything? I added a little something in chat about. I know his identity initially confused me, so I thought it might confuse other people. But the theta is just the angular frequency times a time. So next case n. So that just any angular frequency, because it's angles per second times a time, which is in seconds, gives you an angle. So that's where the theta comes from. So for Fourier series, problem 9, we're going to consider a linear time invariant system that has an impulse response of h of n equals 1/3 to the n times u of n. So anytime I see this form of an equation, I immediately start thinking geometric series. The first part we're going to be asked is to what is the frequency response? So we're going to basically perform the Fourier series for this impulse response and put it in terms of h of e to the jw, which you will start seeing this terminology a lot as we go into Fourier transforms and Laplace and all that. So again, like I said, when I first see this thing, I start thinking geometric series, and this equation to lets us know our geometric series converges. So we're asked to find h to the e to the jw. So our general form for h e to the jw is this: your summation of the h of n times e to the negative jw n over all of time. So I think that's right, but anyway, it might be just one period. Anyway, it really doesn't matter because we converge. So we plug in h of n. So we have 1/3 to the n times u of n times e to the negative jwn. This u of n removes all of our negative terms. So we're back into this, which looks a lot like this equation, this form up here. Well, first we have to put in, we can put the e to the negative jw in by combining the, it's again the product rule of exponents. So we can get a common base here because these are both to the n. So we just put it in to the n, and that's this is our geometric series. So using that geometric series equation, we're able to just move it over into this. This is our h times e to the negative jw function. So hopefully that makes sense on how that all came about. So now we have our impulse response in the domain we want it to be. That way we don't have to perform a convolution integral. We can just use multiplication. So problem B, or part B, gives us the input coefficients. What the heck's happening here? All right. No, that's awesome. So part B gives us the input, doesn't give us the input signal. It just gives us the input coefficients of the Fourier series of the input signal. So these are our input coefficients, and it also gives us our fundamental frequency omega naught, and then asks us to calculate what our coefficients for the output are. So I don't think this is in the this equation is in the study sheet, but your BAKs for your AAKs for both continuous time and discrete time are good things to have. So you may want to, I know they were good things to have when I took this test, so you may want to make sure you have this general equation. We know that our fundamental period is pi divided by 2. Oh no, when we knew omega naught's 2, not pi divided by 2. Sorry. We have two k's, 1 and negative 1. How did she go? Hold on a second. All right, there's a I don't know how she went from. All right, I got lost for a second. I thought omega naught was 2. Back to here. So anyway, because the key is written like omega naught is 2 or pi half. I think she meant to give a fundamental period of 2, which would then give you anyway, I'm sorry. Moving on. So this is B1 is AK, which is just this 1/2 times e to the j pi divided by 4 times 1 over 1 minus 1/3 e to the negative j pi divided by 2. So this is k is 1 and omega equals pi divided by 2. Again, that's the whole, how does this, I'm going to have to get back to you on how that happened. Because when I read it as pi divided by 2 and just saw our fundamental frequency. So anyway, B negative 1, 1/2 e to the j, or k is negative, or oh, I see. This the pi halves comes from the coefficients we're given. It's basically pi divided by 4 times 2 to get your omega from your omega naught. So we know k is 1, omega naught is 2. So that's where this angle comes from, is pi divided by 4 times 2 times the k. So be sure to convert your omegas from omegas to omega naughts, is basically the crux of what I did wrong here. This should be omega is equal to pi divided by 2, not omega naught is equal to pi divided by 2. And that comes from our coefficients. So hopefully that makes sense. But we know the coefficient here. This is just a of k, or which is a of 1, times our h of e to the jw, evaluated at an omega of pi divided by 2 and a k of 1. And this is our h of e to the jw evaluated at a k of negative 1 and omega of pi divided by 2. So that's where those come from. For part C, we are asked, where did you do that? Anyway, for part C, we're asked to calculate the Fourier series representation of y of n. So this is if we were to have the initial x of n and have the initial h of n and do the convolution and get y of n, and then take the Fourier series of that y of n, is what this would be. This will get into, I don't think they do inverse Fourier series too much, but you'll see it a lot when you go to Fourier transforms, Laplace transforms, Z transforms. You'll do the inverse and get the actual equation y of n. In this particular instance, we're not asking for that. So we know the general form of a Fourier series is y of n equals the series times the coefficients times this equation, e to the j k omega naught n, or omega n. So we know B1 is EJ pi divided by 2n. We know B2, actually B1 is this horrible looking coefficient, and P negative 1 is the other horrible looking coefficient. So you have these horrible looking coefficients and this horrible looking coefficients times we know omega naught was, or omega is pi divided by 2 from above, where I got lost and missed it for a minute, but that's where that comes from. So then we plug in the B1 and the B2 and explicitly write the series. So this is basically A1 here. This is your impulse response evaluated at omega of pi over 2 divided by and k of 1. And then this is your B1 coefficient. Or, well, this and this is your B1 coefficient, but I guess it's kind of, this is the added part from B1. So this is your A negative 1 coefficient. And this whole thing is your B1 coefficient, which we can substitute in with this. This is your, again, your impulse function evaluated at pi equals 2 and a k of negative 1. So the big things to look for here are these little negatives that go away and come back due to your k values. So dropping those is easy and easy to miss. Yeah, maybe that's where I got it, because the file I brought up. Yeah, okay, that is where I got omega naught. So sorry. This thing I put up was wrong. This midterm practice. This was actually from when I took the class a year ago because I didn't download it from your guys' file. But when I worked the problem, I did it from your guys' file. So that makes more sense. Thanks, Brad. You're right. This is wrong. This should say pi divided by 2, and that's where omega naughts come from. So that should take a little, makes me feel a little better at least. So never mind what I was saying about the coefficients and all that. This is omega naught. And these are all evaluated at omega naught. Anyway, that's pretty much it for that problem. I'm going to, anybody have any questions? Brad or Virginia, you're in the thing. I'll unmute you and ask you if you're, well, you have to unmute yourselves. I'm sorry. Anybody have anything? Does Colby want us to go over a power, or is he good?
I don't think he does, because he said that he doesn't have any questions with power. He didn't really focus on it during studying.
Yeah, I mean, it's just be able to use the equation. I think it's more, shows up more in the second half, but I can't remember whether or not it's on the exam or not. So
honestly, I mean, I took this class last summer, so that's not that long ago, and I don't remember questions about power and energy coming up at all, really anywhere except for like the homework. So they're pretty straightforward. They're the same thing as stability, but you have a square of your system response instead of just your system response, and it's the same concept though. Kobe says he's good.
All right.
In the YouTube channel.
All right. If there's anybody else has anything, I'm gonna call it a day and start working on my own work.
All right. Thanks for joining us, guys, and hopefully we've answered your questions. If there's any other lingering questions that you think of after we close out this video, feel free to post to Piazza. I'll be here all night. Well, actually, no, I'm going to be going to the grocery store soon. But anyways, I'll be back in a couple hours for sure, and James will be here too. We can, we'll be monitoring the Piazza.
I'll be on Piazza, and if you want to get hold of me on Hangouts, I'll be on Hangouts as well. I just always usually leave that open when I'm doing work, and I'll be doing a lab all night for 334. So anybody need anything, feel free to reach out to me. I'll try to help as best as I can. All right, we're going to stop the broadcast.